Hey, we are going to move away from z-scores or hypothesis testing with what we call a single sample z-test today and into a test that's actually more frequently used in practice called the t-test. And it has a different name because we use a different test statistic. So in the past, you've been computing a test statistic for your sample that you denoted with the letter z. And then you mapped that onto a standard normal or z distribution. And in the t-tests, we will be computing a very similar test statistic, but we call that statistic t. We denote it with the letter lowercase t, and we map it onto a corresponding t distribution. Otherwise, all the other steps of the testing will be pretty much identical. They get a little more complicated, but we'll work through that. So just to brighten spirits at this point in the material, I know we're about halfway through, and when I'm teaching this class in the classroom, I know things are starting to drag. It's just about midterms. So I have this lecture that just has some cute pictures of my dog, Fisher, if you remember, and we'll use Fisher in our introduction to hypothesis testing. So we'll be covering specifically a t-test for a single sample in this lecture, and there are other forms of t-test that we'll cover in future material. And for that t-test, we do need to estimate population variance and standard deviation from the sample. And I'll talk about why we need to do that in a minute. We'll also review symbols, because I'm introducing a whole bunch of new symbols. And you know we already have a bucket full, so I'll just make sure that we do a good review of those symbols. And then we'll finish up the t-test by determining critical cutoff values and calculating a t-score. So let's get into it. Up until this point, we have worked with example problems or research questions where we know the comparison population mean and variance. So we have our sample, and we want to know if our sample represents a population that's distinct from some known general population value. And in the real world, we rarely do know the true mean and variance or standard deviation of the comparison population. It's very unlikely that we would have access to that information in the real world. And in this situation where those characteristics are unknown, we have to use a t-test. We can no longer use the z-test because it relied upon information being known from the comparison population. So we're out of luck. We can't use the z-test anymore if we don't have that information, and we must use a different test, and that test is the t-test, using a test statistic called student's t. Just a little bit of fun history. This test is called student's t-test because there was the individual who came up with this testing method. His name we now know is Gossett, but he was working at Guinness at the time. He was kind of a statistical prodigy, and he was, many years ago, he was working at Guinness. I think he was pretty young, about 19 or 20 years old, and he discovered this testing method. He imagined it. And he wrote it up in a manuscript to be published, but he couldn't publish it with his real name because he was working for Guinness, and he had signed contracts saying that he wouldn't publish any of their intellectual material, right? And because he was an employee of Guinness, he couldn't publish under his own name or he would get in trouble or fired from his job. So he published it anyway, knowing it was an important contribution to the literature, but he published it under a pseudonym, Student. So for many years, we just knew this test as student's t-test. And for t-tests, we don't know, again, the characteristics of the comparison population. So we'll have an extra step as researchers. We are going to have to estimate those population characteristics from the sample values. Specifically, we'll use what we call an unbiased estimate for population variance based on the sample, and we'll calculate that and talk about it in a second. And for the time being, we are going to work with the assumption that we know the mean of the population, but not the variance. So in our example today, we'll test whether my dog, Fisher, is significantly cuter than the average dog. And the research hypothesis in this scenario is that the mean cuteness score for participants in my study who rated Fisher, so they were looking at photos of Fisher and rated him on a cuteness scale, that the mean of those ratings will be higher than the mean cuteness ratings for individuals in general who are rating dogs in general. So for my study, I randomly select 16 people. So my N, or my sample size, is 16, and my sample cuteness rating, they gave Fisher an average rating of 21 on the cuteness scale. So I'm collecting information. I know N is 16, capital M, my sample mean, is 21. And let's say that I also happen to know that the average cuteness score for the comparison population for people who rate other dogs, people typically think dogs are about 17 on the cuteness scale. Could this difference be due to just chance, right? So maybe my sample happened to rate Fisher a little bit higher, but it doesn't necessarily mean that Fisher is significantly cuter than the average dog. Or is my mean high because presumably Fisher is actually in the real world cuter than the typical dog? So to figure that out, we want to compare our sample ratings to the population mean. And we will say it's reported by a national newspaper. Okay. So the newspaper, unfortunately, destroyed the original surveys, and they didn't ever calculate the variance or the standard deviation. So I can't do my z-test. Again, I'm out of luck. I can't do the z-test if I don't know that comparison population's standard deviation or variance. But thankfully, we can conduct a t-test, which will get us the same information. So we'll use a single sample t-test, or sometimes called a one sample t-test. So how would I actually conduct this test? Well, we need to estimate the population variance and standard deviation. We can assume that the sample variance should somehow reflect, in many ways, the variance of the population. So if you think about it, that should make sense, because if there's a ton of variation at the population level, then when we randomly select samples, there should also be a lot of variation across those scores. But if in the population, there's not that much variation, everything seems to look very similar in the population, then when I reach into that population and grab a sample, things will look pretty similar in my sample as well. Likely, right? So there's some relationship. We know that, and we're going to take advantage of that. However, we can't just borrow directly. The variance of the population will not be identical to the variance of the sample. The variance of the sample is expected to be, it's known to be, slightly smaller than the variance of the population from which it's taken. And this is because extreme values are less likely to appear in my sample than out in the real world. And the example I like to use to envision this is my rock collection, right? I like to collect rocks, as I think many people do. And if you think about it, in the entire population of rocks in the whole world, there are a ton of different kinds of rocks. There's a ton of variation, right? There's really rare gems like diamonds and opals. I don't know if those are considered rocks, but there's really rare gems. There's a ton of variation in the different kinds of rocks. But of course, when I draw my sample, my little collection of rocks, I'm less likely to be able to collect those very rare gems, right? So if I go out and collect rocks, because those gems are rare, I'm less likely to come across them in my sample. So my sample ends up being less variable, right? There's less variation in my sample than there exists in the actual population. So you could also imagine it this way. If we think about it for a second, if I have this population in front of us, these hearts, and I randomly sample 5 hearts from this population, we can see that some colors are more rare than others, and I'll therefore be less likely to grab them in my handful. So if you just look at them, think to yourself, if I reach in and grab a handful, I'm most likely to get what colors? Probably the orange hearts, right? Maybe the green hearts. I'm less likely to get a blue or a brown heart. And in fact, if I reach in and randomly sample from this population, I could end up with 3 orange hearts and 2 green hearts and no rare hearts. So you can see that the sample is not as variable as the original population. So just another visual demonstration of this. If the population, the top row here, is really spread out, then we expect that the variance of the sample, which you can see right below it, will be similar in shape, right? The variance will be similar but smaller. So all of these distributions on the bottom row are not quite as wide in the tails as their corresponding top distribution. You can see that. So in other words, the variance of the sample would be a biased estimate for the population. And you can see that because if I just take the variance of the sample, it's not going to be big enough to be an estimate for the population. It's biased, it's wrong. It is systematically going to underestimate the variance at the population level. So we need some sort of solution. Right? What can we do to make an unbiased estimate? Well, we know that we could change the formula that we would typically use to calculate sample variation. Let's tweak it a little bit and see if we can use the same information, but inflate the information so that we think it's a pretty good estimate now for population variance. Typically, the way that we would estimate sample variance would be using sample variance SD squared, if you remember that. That is the variance of the sample is capital SD squared. If you remember, the formula for that is everything that we see down here except the denominator would just have an n. So capital SD squared, the sample variance, is the sum of squared deviations divided by n. Well, how could we alter that formula to inflate the value of the variance a little bit? We could divide by a smaller number. So we tweak the formula so we're dividing by n minus 1 instead of just n. And this will give us an unbiased estimate for population variance. And we call the unbiased estimate of population variance capital S squared. So that's new terminology. Another piece of new terminology is the term degrees of freedom. And degrees of freedom for this test is actually n minus 1. So sometimes you might see that formula written as the sum of squared deviations over df. So equals df. Sometimes you see it written that way. Degrees of freedom in this case is always equal to n minus 1. So if you ever see that df, know that it's your sample size minus 1. Degrees of freedom technically is defined as the number of scores in the sample that are free to vary. So if you think about having a group of numbers in front of me, if I know the mean of that group of numbers, and then I know all of the scores except for one person, there's one person who refuses to tell me their score, or I lost it or something. So I have the mean and everybody except for one person's score. I know that that person's score must be a very specific value. I could figure out what it must be based on the other information that I do know. So that last value is not free to vary. It has only one possible value once I know the mean and once I know all the other scores in the sample. And n minus 1, in that case then, everybody except for 1 has scores that are free to vary, but then finally that last score can't be any value to produce that sample mean. It must be only one score would fit in that data set to produce the known mean. Okay, so we write our unbiased formula then sometimes as over here on the far right. Our estimated population variance, S squared, is the sum of squared deviations. Remember, the sum of squared deviations over degrees of freedom, or n minus 1. I like to remember S squared as being the term we use for the estimated variance because it sounds like that, right? So S for estimated variance. And as always, once we have calculated the variance, we can just take the square root of that value to get the corresponding standard deviation. So the standard deviation of the population is S, and that will be equal to the square root of the sum of squared deviations over degrees of freedom. Okay, so let's review. That's a whole bunch of symbols, maybe like shake it off, get up and stretch or something. And I'm going to review these symbols. Symbols for variance you can see on the left side of your screen, and symbols for standard deviation that we've been introduced to so far on the right side of your screen. So now we have seen 4 of each of these terms. We have the sample variance and standard deviation with the capital SDs, right? Population variance, when it's known, that's the known population variance, is sigma squared. The estimated population variance, which you saw today, is capital S squared. The estimated population variance, capital S squared. And you just saw the formula for calculating that value. And then finally, we are going to use a variance of the distribution of means for the t-test. So we actually could think about having, you have seen sigma squared sub m was the variance of the distribution of means for the z-test. So now we have S squared sub m, which is the variance of the distribution of means for the t-test. And we're using the letter S because it comes from the estimated population variance. So an important distinction, making sure we're not getting confused, we use the formula on the left here to estimate the population variance. Right? So we're dividing by degrees of freedom n minus 1. But when figuring out the variance of the distribution of means, we divide the population variance by n. This formula should look familiar to you from back when we were doing our z-test, right? The variance of the distribution of means for the z-test was equal to the variance of the population divided by n. So if we wanted to know the variance of the distribution of means, which we need to use for our statistical test, then we could calculate that by dividing the variance of the population by n. We're doing the same thing here, except we're using the estimated variance of the population. So we're dividing the estimated variance of the population by n still, that doesn't change, to get the variance of the distribution of means. So the symbol changed here, but the process hasn't changed. Alrighty, so finally, one of the steps that will be a little bit different in our hypothesis testing is determining the critical cutoff values for the t-distribution. When we're using an estimated population variance, now we're using a t-distribution instead of the normal distribution as our comparison distribution. So our distribution of means is now distributed as t. And the t-distribution should be a little familiar looking. It's not too different from the normal distribution in shape. However, it does have slightly fatter tails than the standard normal curve. And in fact, the smaller your sample size, the fatter the tails. So that's kind of interesting, right? The t-distribution changes shape slightly depending on your sample size. That was not true for the normal distribution. The normal distribution is the same shape all the time, no matter what your sample size is, right? The t-distribution changes slightly. It varies a little bit in shape depending on the sample size. And you can look at this diagram to see exactly how it's changing shape. As sample size and corresponding degrees of freedom, because that's n-1, increases, the t-distribution will approach the shape of a normal distribution. They'll be very similar. And as a common rule, as long as degrees of freedom is about 30 or more, the t-distribution looks pretty similar to the normal distribution. So how does this affect how we determine the critical cutoff value for our statistical testing? Well, if you think back to when we were conducting z-tests, we knew the population variance, so we knew that our distribution of means would be distributed as a normal distribution. That's our comparison distribution was a normal distribution, which is always the same shape. So we know that if we're using a significance level of 0.05, our critical cutoff score is positive or negative 1.64. That was straightforward because the normal distribution never changes shape. However, when we're in t-test world with unknown population variances and estimated population variances, therefore, we know that the t-distribution is our comparison distribution and that it's going to change shape depending on the sample size or depending on degrees of freedom. So in order to figure out our critical cutoff score for this test, we need to know first the exact shape, the specific shape of our comparison distribution. And we can figure that out based on degrees of freedom. So we'll look into a similar table. It's very much like the Z table, but it's called a T table to find the critical values. And to find the critical value in that table, we'll need to know the significance level of the test. So whether we're using a 0.05, 0.01 alpha level. We also need to know whether we're conducting a one-tailed or two-tailed test. And then finally, we have to know the degrees of freedom. This is a little screenshot of what that table looks like. You can see that there's a column over on the far left that's called DF. And that's where we'll locate our studied degrees of freedom. So if you recall that in this little example of Fisher's cuteness levels, our sample size for this study was 16. N equals 16, which means that N-1, or degrees of freedom, is 15. So I find 15 in that column. I know I'm conducting a one-tailed test, and I'll use the 0.05 alpha level. Those were determined by me as the researcher. And with all those pieces of information, I find that my critical cutoff score is 1.753. That means that once I conduct my test fully and calculate my sample test statistic, if it falls beyond a critical cutoff value of 1.753, or in other words, if it falls in this rejection region, I will be able to reject my null hypothesis. And in step 5 of statistical testing, we actually go ahead and calculate that test statistic. So we'll calculate our t-value, and we'll use a formula that's very similar, it should look very familiar, to that of the z-score. So you'll notice that t, our t statistic, is equal to the sample mean minus the population mean over standard error. That is the same, actually, when you listen to it verbally, it's the same as the formula for the z-statistic. Sample mean minus population mean, the comparison population mean, over the standard error. And the standard error in this case is what makes the formula look slightly different. The standard error here is the standard deviation of the distribution of means, but based off of our estimated comparison population variance. That's why we're using the capital letter S here instead of sigma. And that's the end of this. In another video, I will be walking through all the steps of hypothesis testing, and we'll find out if Fisher actually is significantly cuter than all other dogs.